Hello, my name is William Neely, and I was a simulation engineer for this project. So the motivation for this project was to simulate a simple autonomous navigation in a controlled maze environment, kind of how robots and self-driving systems learn how to avoid obstacles and navigate through mazes and other courses like that. So my job was I was responsible for building and testing the maze environment the Q learning agent was trained in. So I created a grid workout using the NumPy array. And in the NumPy array, I used ones to represent the walls, the zeros to represent free spaces. And right here shows the start position and the goal position. So I would end up making the custom maze using the maze envelope class, the custom maze envelope class using the gymnasium. So this environment gave me four possible actions: moving up, down, left, and right. So if right here in this function right here, I'll end up making it the if statement so it can move up, down, left, and right. Now I'll also end up making step, reset, and render functions. So in this go right here, you see that I define the reset, and right here, it also shows that if I think the next cell is open, move there. If it stay in place, there's a wall stay in place, so that's where the zero represents. So I would also end up putting in the rewards function. So if it moved in the most optimal way, I'll give it 10 points. If it did not, I'll give it -1 point. So if this way it would learn faster. So and this grid shows what the ones would be represented in the maze. So ones equal hashtag, zeros equal dots, and this is the start, goal, and where the robot is. So this shows the maze, and where the robot is initially is right here, and this is where the goal is. So thank you for your time. I'll pass on to the next person.
So I am Dylan Sadahu, and this is my portion of the project. So my role was to implement the reinforcement learning algorithm using Q-learning and connecting it to the maze environment that William built. So I created an agent that uses a Q table to store the expected values, to store the expected value of the action that the character will take at each step of the maze. And so the Q table is created right here. And so during training, the agent interacts with the environment over many episodes, and at each step, it selects an action using the epsilon greedy strategy that's shown right here. This is the epsilon greedy action selection strategy. And basically, this strategy makes it so that sometimes the character will explore randomly, and sometimes it'll go based off what it's learned already. And so, after each action, the agent updates the Q values using the Belmont equation, which is right here. And basically, with the Belmont equation, it adjusts its knowledge based on the reward it received and the estimated future rewards. And so over time, the epsilon decays so that the agent can gradually shift from exploring, fully relying on randomness, to only using its learned behavior. And by the end of the training, the Q table converges to an optimal or near optimal point at which I can then save it so the agent can navigate the maze without having to use retraining.
Hello, I'm Donna Moses. I serve as a model optimization specialist. My job was to connect the simulation environment to the algorithm and ensure the agent learns the maze efficiently. To make this efficient, I implemented a epsilon greedy logic. With decay, the agent starts with a 100% exploration to map the maze, but gradually decays to 0% randomness. This tuning forces the agent to stop guessing and rely on what it's learned from experience, ensuring it gets the shortest path every time. It's built to run 2,000 episodes by applying the Bellman equation. The agent updates his Q table, allowing to learn the value of the move based on future rewards rather than just immediate feedback. Here is the result it gives right here. Thank you.
Hello, everyone. As a data analysis and project lead, my primary focus was evaluating our trained model and generating the final performance matrix. To prove our Q-learning algorithm actually worked, we first had to establish a worst-case scenario. I wrote an evaluation script to track a purely random agent over 1,000 attempts that random baseline averaged about 144 steps to solve the maze. Next, we tracked our trained model. As you can see in our learning curves, the agent initially struggles, but as it updates its knowledge, the reward sharply increases and settles once it locks into an optimal path. When we ran the fully trained agent, the efficiency gains were massive. It condensed the maze traverse from 144 states baseline down to an optimal limit of just about 8 to 10 steps. That can be seen here. Ultimately, our data confirms that the model successfully learned the optimal policy.